So let me give you the solutions to some in-class practice problems. First one being a 13-gram bullet that's moving at 230 meters per second, hits this block, but then it passes right on through it. And after passing through it, it's moving at 170 meters per second. So we're going to find out the speed of the block. After this interaction, M1 is the bullet, M2 is the block. All right, so we start with our standard conservation of momentum equation for two bodies. Three bodies, of course, we just have additional terms on both sides. And we have that nothing goes away except for this term. But I'm going ahead and solving for V2 prime. V2 prime is what we want. And there's the algebra. And mass 1, small amount of mass for the bullet, V1. M2, V2, 0. M1, V1 prime, all positive. Mass 2, 2 kilograms. And out pops 0.39 meters per second. What you had to realize here that this is a momentum problem in that we have an interaction. It's not perfectly elastic. It's not perfectly inelastic. It doesn't stick to it, doesn't bounce off it, but nevertheless with the data we have, it was relatively simple to just plug and chug and come out with our answer. So in our second problem, we'll take a 5,800 kilogram railroad car. That's pretty small, right? Doesn't matter. Moving at a constant speed of 8.6 meters per second. Snow begins to fall and lands vertically, filling up the car. At this rate, 3.5 kilograms every minute, snow is falling into the train, into the car. So we're going to assume frictionless rolling. We're going to figure out the speed of the car after 90 minutes with that snow continuing to fall into the car. Well, the key here is to recognize, and in fact, the type of interaction we have here is an inelastic collision. There's really no difference between this problem, this continuation of snow falling, and a big snowball with the collective mass of all the snow that's going to fall dumped into the car all at once. The vertical motion of the snow doesn't affect anything, at least for this problem. This is a one-dimensional problem, and plopping that snow down vertically into the car doesn't have any direct effect on the horizontal motion. But what does have a direct effect is the inertia of that snow. It isn't moving horizontally until it collides with the car. Hope that makes sense. So we'll start with our basic conservation of momentum situation. Recognizing that since it's inelastic, we have the velocity after being just v prime. That's experienced by mass 1 and mass 2, both the train or the car and the snow. So then, let's figure out what M1 is. We don't have that. M1 being the snow. I'm sorry, M1 being the car, 5,800 kilograms. M2 being the snow, and we have to figure that out. So it's going to be 3.5 kilograms per minute times 90 minutes. And that'll give us the kilograms. So 315 kilograms of snow. That's what's colliding inelastically with a 5,800 kilogram car. So now, solving for this velocity of the whole system, we just divide both sides by this, and we get this expression. Now it's time to plug in numbers. I think all these numbers look good. 315 times 0, because initially the snow is not moving, okay, over the total mass. 8.16 meters per second. So here is a problem that's just slightly more challenging. We're going to have a bullet that's going to hit the block. It's going to embed itself into the block. It's 15 grams. We need to figure out how fast the bullet was moving before it struck the block. The other information we have, however, block is stationary to begin with, is that there's a coefficient of 0.25 and the block slides 9.5 meters before coming to rest. So that's the information we have. So we're going to use that to figure out how fast the bullet went. Well, it's a two-part problem, and we have to kind of work backwards. Yes, we can use momentum to consider that this 15-gram bullet hits the block and makes the whole thing move, but how fast does it move? We need some information to figure that out, but we have it. In fact, we need to figure out how fast this block has to be moving so it slides 9.5 meters with this coefficient of friction. Then, once we know what that speed is, then we can figure out the original speed that this had to have to make it move that fast. Sounds like a plan? Let's go. It's an inelastic collision. Okay. And so this is what I had just said. Find the speed or velocity required to slide that 9.5 meters and then use momentum to solve for the initial speed, this v of the bullet. So we can use this constant acceleration equation. That should work for us. Where the block comes to rest, we need to know what this is. So v0 squared is equal to 2ad. And the acceleration is the sum of the forces, which is friction, only friction, over the mass. There we go. So that's 2 times friction is mu kmg, and we're dividing by the mass. So that leaves us with 2 mu kgd. We have all the information we need for that. That's v0 squared. That's the initial velocity of this squared. So let me go ahead and solve for that. 2 times 0.25 times 9.8 times 9.5. 46.6. Take the square root of that. And the initial speed of the block has to be 6.82 meters per second. Now that we solved that problem, now let's use momentum to solve for the inelastic collision. And particularly, we're looking for this initial speed here. Now that we know this, and we know all the masses, and we know that this is 0, we got everything we need. Here we go. V1 is m1 plus m2, quantity times v prime over m. And there is plugging in the numbers. The mass total, that 15 grams didn't contribute much, but a little bit. And here's the speed or velocity of the block after the impact, and there's m1. This is really small, and that's going to make that speed pretty big. Namely, 507 meters per second, which is the answer we were looking for.